Okay, I'm going to go through the answers for the unit practice test. So the first one here says it's a hydrocarbon and it's burned, so we're talking about combustion analysis. So you say 88 grams of CO2, 36 grams of H2O. Hopefully this kind of hits you in your head. Okay, well I know CO2 is 44 grams per mole, and hopefully you know that water is 18 grams per mole. So when you see 88 grams, you say, well, that's 2 moles of CO2, which means you're going to have 2 moles of carbon, and 36 grams of H2O is 2 moles of water, and that's going to give us 4 moles of hydrogens. Okay, so if I have 2 to 4, then my ratio is C2H4 or CH2, and that's my empirical formula. Answer B. Okay, for number 2, you've got an Alka-Seltzer tablet. Okay, 3.4 grams. We'll need that later. Okay, and what do we really have? We have 0.089 liters of CO2 at STP. Okay, so we're going to use that information. If I know my CO2, I can find my sodium bicarbonate. And if I know my sodium bicarbonate, I can divide by the Alka-Seltzer tablet times 100 and get my percent. So to set it up, so we have 0.089 liters of CO2. We know that it's a gas, so 22 liters for 1 mole of CO2. From the balanced equation, we can see for every 1 mole of CO2, we get 1 mole of sodium bicarbonate, and we want grams of that. So 1 mole of sodium bicarbonate, NaHCO3, you add that up, that's 23 plus 1 plus 12 plus 3 times 16, which is 48. That comes out to be roughly 100 grams of sodium bicarbonate. Now, the trickiest part we got to do right now, and also the last part, is we want it to be a percentage, so we're going to divide by 3.4 grams of the Alka-Seltzer, and we're going to multiply this whole thing by 100 to get it to be a percentage. So we got to solve, let's get this out of the way, we got to solve this. So what do we have? We have 0.089 times 100, so that's going to be like, I'm going to change colors, that's going to be like 8.9, okay, getting rid of those two numbers, and I'm going to do times 100. Okay, divided by 3.4 and 22.4. Okay, so this top number, okay, what I have 3.4 and 22.4. Okay, so what you can see what's going to happen is this will kind of go into there about 5 times. And 3.4, 8.9, that'll go in there roughly, oh boy, I would say, you know, if this was 8 and this was 4, go in 2 times. So it's really going to be somewhere between 2 and 3. So let's say 2.5 times. Okay, so 2.5 times 5 would be about, 12. So I need a number somewhere in that range. And so here we have 10. So if I had a calculator and I can actually do it out, I would say, okay, I can see it's going to come out to 10%. But I'm getting an answer about 12%, so it's certainly closer than 4 or 33 or 0.1. So all I have to do is get a rough answer, and I did, so I know it's 10%. Number 3, hydrate. Hydrates, remember, those are chemicals that have water molecules built right in, and this says X hydrates, which means we don't know how many. Is it 1? Is it 2? Is it 5? Is it 8? We've got to figure those out. Now what I would do here for this, for me, I would just try guess and check. So I would say, okay, I got a calcium. Calcium weighs 40. And I know each chlorine weighs 35.5, so that's going to be about 70. So it's about 110 grams just for the calcium chloride. Water we know weighs 18. So if this first one, if I heated it up and the water goes away, then I'm going to lose about 18 out of a total of 110 plus 18. So that's roughly going to be 20 out of 130. Well, a quarter of 130 is half of that is 65, half of that would be 30 something. So this is not the right answer. I know that that's not the right answer. Let's try again. If I had 36 over, that's 2 waters, over the total, which would be 110 plus 36. So 36 out of 146. So what am I talking? Half of this would be 73, half of that would be about 35, 36. So there it is. So that's 36 is about a quarter of this number, so that is my answer. And that's how I would do it. I would just guess and check. Number 4, which of the following would be an empirical formula? Empirical formula is one that cannot be reduced. So looking at this, this has 2 and 2, so that can be reduced. This has 4 and 10, that can be reduced. This has 2 and 6, that can be reduced. It's H2SO4 that cannot be reduced because it's H2S1O4. We don't write in the 1, but you cannot reduce that one. So that's why answer A is the correct answer. For 5, the density of a metal is about 1.5 grams per cubic centimeter. What's the volume of 5 grams? So we just do this. If I had 5 grams, then using unit analysis, okay, I could say that I have 1.5 grams per cubic centimeter. So I just have to work out this problem. And what I can see, what I have, 5 is larger than 1.5. In fact, it's probably about 3 times larger because 3 times 15 is 45. So 4.5 would be 3 times 1.5. So it's going to be larger than 3, but certainly not 6 or 7, and certainly not 0.3. So I can just limit it down to answer C already. Okay, for number 6. This is going back to our lab, understanding our lab. And if we had nickel sulfate, here is its absorption spectrum. So we say which color should we use, and what we're looking for is which one absorbs the most. Which one absorbs the most? So let's look at our graph. Our graph says this is 500, 700, so this is 600, and this would be 800, and so obviously this would be 400. So if we go back and say, okay, at 470, so halfway before 50, a little bit more, so 470 be somewhere around there. 565, well here's 500, 600, halfway is 550, so 565 would be somewhere there. 610 would be a little bit more than 600, so right about here, that's better. And 660 would be a little more than halfway, so 650, 660, I'd say somewhere around here. And we can see that this is where it absorbs the best. Of these 4, that's going to be the best answer, 660 nanometers. So wherever it absorbs the best. Number 7 says if we had a picture, and we didn't draw a picture this time, but if we had a picture, okay, we would have 9 molecules of XY, and out of all those molecules, there would be one that is split up into X plus and Y minus. So we're saying that, and these are floating around in solution. So since it's floating around in solution, we can say, okay, it's not AgBr. AgBr would be a precipitate. We know that because of our solubility rules. Forget that one. We can eliminate HI because that's a strong acid. It would be 100%. It would have 10 X pluses and 10 Y minuses. Same thing for KOH because potassium compounds are soluble, so that would also be split up. So it has to be answer D, HF, which only partially breaks up. It's a weak acid. So that's how that one works. Number 8, the following procedures were performed to prepare a solution of copper chloride that weighs 134.45. Well, this is significant that we're using 1.34 grams. So this is a mole. This is 1/100th of that. So we're talking about 0.1 moles of copper chloride. We're going to dissolve that into 100 milliliters of water, or make a total solution of 100 milliliters, and we're going to say that, well, that's 0.1 liters. I did the top of this wrong. This should be 0.01 moles, that's 1/100th, divided by 0.1, so this comes out to be 0.1 molar. So my solution is 0.1 molar, but in step 2, I take 5 milliliters of my solution and add 5 milliliters of water. So that's going to reduce this down to half of its concentration. So that would be 0.05 molar. So I'm looking for an answer of 0.05. Step 3 just says we're using that in a colorimeter. It does not change the concentration. So that's why the answer is 0.05 molar from step 1 and step 2. On number 9, Okay, we have 1.2 grams of filter paper, 2.2 grams of precipitate with the filter paper, so obviously the solid, the precipitate, must be 1.0 grams of whatever our solid is. Now, implied in this equation is we are mixing calcium acetate with sodium carbonate. So what am I going to get? I'm going to get sodium acetate, that'll be soluble, and I'm going to get calcium carbonate, and that's the one that's not soluble. Okay, so this white solid must be calcium carbonate. Calcium carbonate. So here's our equation. If I had 1 gram of calcium carbonate, what can I do with that? Okay, grams to moles, and calcium is 40 plus 12 for the carbon plus 16, 16, 16, which is 48. That comes out to be 100 grams per mole. So I have 100 grams per mole calcium carbonate. And what I'm going to do now is say for every 1 mole of calcium carbonate, I would have had 1 mole of calcium acetate because of the calciums. Now calcium acetate, Ca, C2H3O2 twice. Now I want to have grams. What's my mass of my calcium? So I have to have one more step, and that is I'm going to take this and multiply by its molar mass. Now what's the molar mass of this stuff here? Okay, so I've got calcium, which is 40. I'm going to change colors. Okay, I've got 2 C2 twice, so I've got 4 12s, that's 48. I've got 3 hydrogens twice, so I have 6. And I've got 2 oxygens, which is 32 twice, that's 64. And when I add that all up, I get 158. So I'm going to multiply all this by 158. Now I just have to do this math in my head. That's grams for 1 mole. So what have I got? I've got 1 times 1 times 1, that's easy, times 158 over 100. So this is very easy. So I have 158 over 100, which is 1.58. Okay, and if I round that off, that's where I get my 1.6. Okay. For number 10, I'm using 0.1 molar NaOH to titrate 200 milliliters of my solution containing citric acid. What is the concentration of my citric acid? So I need to get moles and divide by my volume, which is 200 milliliters. Okay, so I'll start off here. What do I know? I know I have 30 milliliters of my base, NaOH, and I have a 0.1 molar, so that's 0.1 moles of NaOH per 1,000 milliliters. And from my equation, I can say I need 3 moles of NaOH for every 1 mole of citric acid. So this part so far is going to give me the moles of the acid. Well, I want concentration, so I want moles per liter. So I'm going to divide by the liters, which is 200 milliliters, so 0.2 liters. So here's my problem. I have 30 times 0.1 divided by 0.2 and 3. And you can see what's going to happen. That 3 goes into, 3 goes into 30 10 times. 10 times 0.1 is 1, so I have 1 over 0.2. And I always have trouble with that, so I'm going to multiply the top and the bottom by 5. Okay, and this is not correct. Okay, this is not correct because I forgot my 1,000 on the bottom here. That makes a big difference. So again, so I have 3 and 30 gives me 10. 10 times 0.1 gives me 1. Okay, on the bottom I have 0.2 and I have 1,000. Let's forget this for a moment. So 0.2 times 1,000. And so that's going to come out to be 1 over 0.002. So now I'll multiply the top and the bottom by 5, and I'm going to get 5. I'll do it up here. 5 over, if I multiply the bottom by 1,000, I'm going to get, this is not right, 5 over 0.01. 5 over 0.01, which is 0.005. I don't think that's still right. Okay, I went back and tried to clean this up again, so I got my 30.1 over 0.2 1003. So looking at this, 3 will go into 30 10 times. If I have a 10 here on top, then I can take off one of my zeros. So now my problem is 0.1 over 0.2 times 1,000. Okay, I'm going to multiply my top and bottom by 10, so I have 1 over 2,000. Okay, 1 over 2,000. So that is going to end up being, okay, I'm going to multiply both sides by 5 because I get confused otherwise. So this top is going to be 5, and the bottom is going to be 10,000. And so I'm going to move my decimal point back 1, 2, 3, 4 places. So from here I'm going to go back 1, 2, 3, 4 places. And I still get the wrong answer. So I know my answer is A, and I'm just going to have to let this go. I've done it wrong 4 times in a row. Okay, number 11. What is the maximum yield of NH3 beginning with 280 grams of nitrogen gas? This is assuming that you know you take nitrogen gas, you mix it with hydrogen gas, and you get 2 ammonia gas. So there has an implied equation in here. And what we're saying is if we had 280 grams of nitrogen in 2, well, nitrogen weighs 14, but it's diatomic, so it's going to be 28 grams for 1 mole of nitrogen. And from our equation, we can see for every 1 mole of nitrogen, we get 2 moles of ammonia. And we're trying to find grams of ammonia. So 1 mole of NH3, okay, that's 14 plus 3, that's about 17 grams. So 28 goes into 280 10 times. 10 times 2 times 17. Okay, well 2 times 17 is 34, times 10, 340 grams of ammonia. Okay, if we have the combustion of propane, if 3 moles of propane is mixed with 10 moles of oxygen, what's the maximum yield of CO2? So this sounds like a icebox problem. Okay, we don't have to do it that way, but I think it's a convenient way to organize our information. So I just recopied my equation. Now we're not really looking at the water, so we don't have to worry about that. So what I have is I'll change colors, 3 moles of C3H8, and I have 10 moles of H2O. So one of these is going to get used up first. So if I used up all 10, then I would have 5 is to 1 as 10 is to 2. I would need to use up 2 of my C3H8. And I have 3, so that's what's going to happen. So I'm going to use up all 10 of my oxygens. And I say 5 is to 1 as 10 is to 2. So I'm going to use up 2 moles of that. And I'm going to say 1 is to 3 as 2 is to 6. So I'm going to make 6 moles, and I'm going to make 8 moles here, but I don't care. Because my question is, what's this number down here? How many moles of CO2? What's my yield of CO2? And so my yield here is going to be 6 moles of CO2, which is answer B. Okay, 13. Okay, I have some silver nitrate mixed with potassium sulfide. So if I were starting this, I'd say, well, silver nitrate, AgNO3, and I mix that with potassium sulfide, K2S, then I'm going to get silver sulfide, Ag2S, and I'm going to get 2 potassium nitrates, and to balance I would need 2 of those. Okay, but I'm not saying I have 2 of these and 1 of these. I'm saying I have 1 mole of silver nitrate and 1 mole of potassium sulfide. So if I just had an Ag plus and an NO3 minus, and I had a K plus, and an S2 minus, okay, well, that doesn't exactly work because I don't have enough silvers to make silver sulfide. So I'm just going to double everything. That'll still be the same number of moles. So I got Ag plus and NO3 minus. I have K plus, and S2 minus. Okay, so my Ag plus and an S2 minus, those are going to go together to make a precipitate, and everything else is left over. So which of these is the right situation? Okay, looking at these bottom ones, I'm certainly not making KNO3, so I can eliminate C. And I'm not making AgS, I'm making Ag2S, so I can eliminate D. So the answer is either A or B. And the difference is this one has some sulfides left over, which I do have sulfides left over. Okay, and that is going to be the right answer. So answer B, because I have potassiums, I got nitrates, and I got at least some sulfide left over because I don't have enough silver to use it all up. And the key part of here is we weren't saying we were letting these just any amount react. We have 1 mole of silver nitrate with 1 mole of potassium sulfide. That's the situation. Okay, 14. Solutions of magnesium hydroxide and hydrofluoric acid are mixed. Well, we should know hydrofluoric acid is a weak acid. It has to show up as HF. So because of that, I know I can eliminate answer B, and I know I can eliminate answer D. Okay, now the question about the magnesium hydroxide, that is not very soluble. Okay, so what's going to happen is I think I'm going to have to go with magnesium hydroxide being together like that because it does not break up, and I would end up with answer A. When I get to 15, peroxide is heated, it turns into H2O and O2. Which of the following statements is true? Okay, so this is a chemical change because a gas is formed. I would agree that it's a chemical change, and I would also, it's true that a gas is formed, but I would say it's not a chemical change because a gas is formed. Okay, it's this answer here, a chemical change because we are breaking chemical bonds. Now, it is certainly not a physical change, so we can eliminate B and D because it's peroxide before, and afterwards it's water and oxygen, very different chemicals, so that's not a physical change. Okay, but A, even though A is true, this part is true and this part is true, the because makes it not true. Okay, it's not a causal relationship. It's just both those are true. Now, you could say, well, how do you know that it is a chemical change? You would know if you have a gas forming. That's a good clue that it is a chemical change. But the real thing is what's happening is that chemical bonds are broken. Okay, number 16. We have, don't worry about this beginning, we have all these different things with sulfur in it. We would know which one has the highest oxidation state. So we have sulfur S8, we have Na2 S2O3, we have H2S, and that's the same as the other one. We have Na2 S4O6. Okay, so those are our possibilities. So which one is going to have the highest oxidation state of sulfur? Well, this one is sulfur is 0. Okay, this one is sulfur as -2 because we know hydrogen is +2. So we know that this is -2, so that's not the answer. Now what about the others? Okay, you have to kind of say, well, here's 2 Na pluses, so this ion is -2. Here's 2 Na pluses, so this ion is -2. So if we had S2O3 2 minus and S4O6 2 minus, now we can go back and calculate what S is, and we'll do it an algebra way. So 2 times X, which is the number for sulfur, plus 3 times -2 is equal to -2. What's that mean? So 2x plus -6 equals -2. We'll add 6 to both sides. So 2x equals 4. So therefore the sulfur must be in the +2 state. So that means that this one cannot be the answer, S8. If we do the other one, say 4x plus 6 times -2 equals -2. So that is 4x plus negative 12 equals negative 2. If I add 12 to both sides, okay, that's negative 2, not negative 12. Okay, if I add 12 to both sides, then I get plus 10. So 4x equals plus 10. Divide both sides by 4. So x equals 10 over 4 or 5 over 2. And the idea is you can have fractional oxidation states, and it does happen with some of these more complicated chemicals. So that is the answer anyway, because 5 over 2 is 2.5. 2.5 is larger than 2, larger than 0, larger than negative 2. Okay, consider this reaction. What's the driving force? Okay, we should recognize that this is single replacement, and therefore it is a redox reaction. And we have copper neutral changing into copper 2+ and losing some electrons. And we have silver ions turning into silver metal by picking up some electrons. So we have a transfer of electrons. Copper is losing, silver is gaining. So a transfer of electrons from copper to silver. Formation of a solid, even though it is forming a solid, that's not what drives a reaction. Transfer of electrons from nitrogen to oxygen, no, it is transfer, but the nitrogen and oxygens are the same oxidation state on both sides, +5 and -2, and the solubility of silver nitrate, that is not going to help anything. So it's only answer A. Okay, last 3 multiple choice questions. And if a acidified sample of peroxide was titrated with permanganate, and here's what happens: it stays clear, stays clear, stays clear, stays clear, and then all of a sudden it turns pink. So what is the reason we get that pink reaction? Well, you might jump to the conclusion that, well, that Mn2+ that you're forming must be pink, certainly not oxygen, certainly not water. But if that was true, then you would have pink all along. Okay, so where we actually get the pink is when all of the peroxide is used up and we have some permanganate left over, the dark purple permanganate, and a little bit of it makes the solution pink. So the answer is the permanganate is what is responsible for making the solution pink in their final solution. Okay, number 19. Okay, somebody's oxidized, somebody's reduced. So you can see Fe2+ is turning into Fe3+, so that is oxidized. Its number is getting larger. And who's going down? Here's Mn2+, here's Mn in the +5 oxidation, the +7 oxidation state. So the Mn is getting reduced. So that's why it's answer A. Okay, we can eliminate B because oxygen is not changing. Same thing for D. And C is the right elements, but they have them going the wrong direction. So the answer A is the right answer. Okay, the last multiple choice question is we have dichromate changing into chromium. What are we going to have in the balanced half reaction? So we have to just do this. So if we have Cr2O7 2- changes into Cr3+, all you need to have 2 chromiums, so I have that. Now I have 7 oxygens, so I'm going to add 7 waters. I have 14 hydrogens, so I'm going to put 14 H+ on this side. And this gives me a total charge over here of +12, total charge over here +6. So I'm going to need to add 6 electrons on the left side. So the number of electrons is 6 on the reactant side, answer A. And that is the multiple choice test.